Hi everyone, this is Jeff Geisinger, and in this second DIVA tutorial, I will go over how to run a daylight autonomy simulation, and then I'll explain the results that we get in Rhino, both the graphic results that we get for the daylight autonomy in our scene, as well as the DaySim report that is generated when we run this type of analysis. And just to summarize the model that we're using, we are, again, as in the last tutorial, using the MIT Reference Office, which is a simple south-facing side-lit office that's located in Boston. And you could download the Rhino file along with this tutorial. So the first step for running a daylight autonomy simulation is to set the location for the scene. And this is a step that we also did for the previous tutorial. So to do that, in the DIVA 3.0 toolbar, you need to locate the location button and click it. And this usually triggers a dialog box that comes up. If you had previously set a location before, it asks you if you want to rewrite the materials settings for the file. And if you hadn't set any custom materials in your DIVA simulation, which we hadn't in this scene, in this case, you can go ahead and just click yes. If the case is that you've run some simulations and you've actually set up some custom materials in the Radiance file behind the scenes, then you want to click no. You do not want to overwrite that Radiance definition. But since we're using the default materials, we can go ahead and click yes. And that brings up the energy plus weather file dialog, and we can scroll down to Boston Logan and double click that. So that sets the Boston weather file for this scene. And the next step then is to set the nodes for the scene. And the nodes are essentially an array of analysis points that are sensors within the Rhino file that will sense the amount of illuminance for the daylight autonomy calculation. So we'll go ahead and click on nodes. And then what's important here to note is the prompt that comes up in the command line of Rhino, and we'll have to follow these instructions to see what steps we need to take in order to set the nodes. So here it's asking us to pick one or more planar surfaces which will be subdivided for lighting analysis. And so we basically want to select the floor because we want the nodes to be offset from the floor and to match the overall extents of the floor geometry. So I'll go ahead and click the floor, and after left clicking I hit enter. And next, DIVA prompts you to enter the distance of sampling nodes off of your analysis surface in your model units. Okay, so my units are meters, and the default value is 0.85. But I know that in my model, I want this work plane to be just above the actual height of the desks in the scene. And I know that I've measured my desks, they are at 0.86 meters. And so I want to change this distance to just above that value. So for simplicity, I'll make that 0.9 meters. And so that way I know that it'll be just above the actual work plane height in our space. And that way we'll be able to see some values for daylight autonomy that are on top of that work plane. So once I set 0.9, I hit enter. And next it asks to enter the distance between calculation nodes. And the default is 0.425, and I'll go ahead and use the default for the purposes of this tutorial. And so you'll see, if I double click on the perspective view, that DIVA has generated an array of analysis points that are spaced about 0.4 meters apart, and they're just above the height of the work plane. So these are my sensors that DIVA is going to use to calculate the illuminance, and then after calculating the illuminances, it will calculate daylight autonomy for the whole year. So the next step is to set the materials, but since we ran a simulation previously, we'll use the same materials that we had assigned in the previous tutorial. And so for some more instruction on this, you can reference that previous tutorial. So I'll go ahead and close that. And the next step then is to click on metrics. Okay, whereas before we were using a simulation type in the Daylight Images tab, This time we'll go ahead and click on the Daylight Grid-Based tab because Daylight Autonomy is a grid-based simulation. And then you'll see that there are some sub-tabs, and we'll use climate-based. So climate-based simulations are annual simulations that are based on the actual sky conditions recorded in a climate file. And so we'll go ahead and click on that sub-tab. And you'll see that that brings up a series of dialogues. And starting with metric, we want to use Daylight Autonomy. There are other types of climate-based metrics that you can choose, but for the purposes of this tutorial, we'll go ahead and stick with Daylight Autonomy. Since Daylight Autonomy is defined as a daylight availability metric that corresponds with the percentage of occupied time when a target illuminance at a point in space is met by daylight alone, we have to indicate an occupancy schedule, because within this occupancy schedule, DIVA will calculate the target illuminances, the illuminance levels at each sensor point, and decide whether or not those illuminance levels for every hour of the schedule are meeting the target illuminance. And so that's why we have this choice of setting an occupancy schedule. And so for this tutorial, we'll go ahead and click with the default, which is from 8 to 6 with daylight savings time, and this is at 60-minute intervals. So we'll go ahead and click that. And since the definition of daylight autonomy also requires a target illuminance to decide whether or not the illuminance at a given point in time, at a point in space, is meeting this target illuminance, we have to set what that illuminance level is. And so here we input that illuminance in the units of lux. And so the default is typically 300, and we'll leave that as the default. That's a typical target illuminance for an office space. And the standard international units for illuminance are lux. And so we'll go ahead and keep lux as our units. And then we also want to make sure that we have show daysim report checked, and I'll go over that after we run the simulation. The daysim report is one way of communicating the results from our daylight autonomy simulation. And we'll leave the DGP schedules unchecked for this tutorial, and we'll go over that later in subsequent lessons. And then you'll see the next group of parameters are the advanced parameters. And the first line under advanced parameters is the radiance parameters. And so here you can set the complexity of the scene in radiance for how radiance is going to be calculating the backwards ray tracing, determining the number of ambient bounces and levels of ambient light, and the ambient divisions for the scene, as well as subsampling, supersampling, ambient accuracy, and so forth. For this tutorial, what you really have to focus in on is the number of ambient bounces. The default, I believe, comes up as 2, and for this tutorial, I had changed it to 4. We should be using at least 4 bounces for daylight autonomy because this higher level of ambient bounces will also allow us to do a more accurate visual comfort analysis in the next lesson, and then again do a more accurate daylight autonomy calculation for applying dynamic shading in a subsequent lesson. And so be sure to go ahead and change that ambient bounce value to 4. So the next parameters for the under the advanced section have to do with adaptive visual comfort, and we'll just leave the default for now because we actually don't have any visual comfort criteria for this run of daylight autonomy. And you could leave the geometric density and clean up temporary directory as the defaults. And when you're ready, you can click Run Simulation. And this will bring up a command prompt that will take several minutes to run, especially since we have 4 ambient bounces. It'll take a little bit longer. And I'll let this run and then return to the tutorial once it is complete to go over the results. So when the simulation is complete, a dialog box pops up that's the Load DIVA Metrics dialog box. And you'll see that you can choose which lighting test you want to pull up. Because DIVA is running daysim based on daylight coefficients for the scene and the geometry within the scene, you can actually run several different types of lighting tests based on the calculation we just ran. But for this study, we'll go ahead and keep the default value, which is the daylight autonomy SDA metric. And you'll see that it tells you where the results file is located. The results folder is located right next to the Rhino file that you're using to run the analysis. In my case, it's in the desktop, and I'll go ahead and pull up the desktop. And we'll see that here in the desktop, I have my Rhino file, which is the reference office T01. And if I double click on that, you'll see that there are 4 subfolders. Whereas last time we were looking at the visualizations, this time we have our files saved here in grid-based. And you see that running a daylight autonomy simulation yields 5 different files, and these are sort of behind-the-scenes files that DIVA will use to actually represent the results. First, you'll see that there's an HTML file. Once I accept the type of results viewer that we want to use, you'll see that an HTML file will pop up, and that's located here. And the other files are kind of behind-the-scenes information that DIVA will use to visualize the results, and we don't really need to go into those in any more detail for today. And so back to the Load DIVA Metrics dialog box, you'll see the next set of information is the visualization options, and it asks for you to pick a color scheme. And I'll go ahead and use the default color scheme from blue to yellow to red, and it asks if you want to label specific nodes, and I'll go ahead and click Label All Nodes. This way we'll see, along with the colors, with the colors that are mapped within the work plane that we set, we'll also see percentage values, because daylight autonomy is actually a percentage of the occupied hours where those spaces are meeting your target illuminance. And so this is the Label All Nodes box that I'm going to check, and I'll leave the rest of these values unchecked, and I'll go ahead and click Load Simulation Data. And you'll see that when I click Load Simulation Data, it pulls up an HTML file that I mentioned before that is saved on your local project directory. And this report is called the DaySim Simulation Report, and it tells you some statistics about the simulation that you just ran. And the first line of information under the DaySim Simulation Report is the daylit area. And the daylit area is the area of the room at which the spatial daylight autonomy corresponds to at least 50%. And that means that at least 50% of the occupied time, the daylight levels at that point are above the target illuminance. And so you'll see that for this space that we studied, 43% of the floor area is considered daylit. So 43% of the floor area has at least 50 daylight autonomy value of 50%. And the next line underneath the DaySim report is the mean daylight factor. And so daylight factor is the ratio of interior illuminance levels to exterior illuminance levels during overcast sky conditions, and that is at 2%. And next, the occupancy is indicated, and that's really just based on the schedule that we selected. And since we had from 8 a.m. to 6 p.m., DaySim is showing that it's considering 3,650 hours per year. And then the next line is glare, and you may or may not have actual information for glare. And the reason why it's showing up here on this DaySim report is because I had previously run a glare analysis for this scene, and it's okay, you probably won't have information for glare, and we'll go over this metric in a subsequent tutorial. So for now, we don't have to really go into any detail. And so below we have some more in-depth information about the performance of the scene. And the first is the daylight factor analysis. And this daylight factor analysis has a bit to do with a previous version of LEED. That previous version of LEED for the daylighting credit, or one option for that credit, has to do with daylight factor compliance. And since the new version of LEED actually has as one of its compliance paths, it has actually daylight autonomy as a way to meet that daylighting credit. This daylighting factor line is really no longer really relevant or useful for the newest version of LEED. And you'll see if you run different types of climate-based metrics, one of the choices is to do the spatial daylight autonomy that is specifically corresponding to the daylighting credit in the newest version of LEED. The next line in the DASIM report and under these more advanced results is the daylight autonomy analysis. And here it shows you it shows you the mean daylight autonomy. So whereas before we were looking at daylight area, here it's showing you the mean daylight autonomy. So it's giving you the mean across all of the sensor points in your space for daylight autonomy, and that is 41%. And here it says for active occupant behavior, and that really just means during our occupancy schedule. And the next line summarizes the daylight area that we had gone over before. The next line is continuous daylight autonomy. Now, continuous daylight autonomy is similar to the spatial daylight autonomy that we ran before, except it gives partial credit for daylight values that are below the target illuminance. Whereas the daylight autonomy, the default daylight autonomy really is a kind of binary where it gives no credit or full credit if the sensor point is meeting the target illuminance. And so here again it shows the mean continuous daylight autonomy. Since it gives partial credit for areas that are below the target illuminance, you'll see that it's the mean continuous daylight autonomy is higher than the spatial daylight autonomy mean. And so the next sentence is the percentage of sensors with a daylight autonomy maximum greater than 5% is 39% for active occupant behavior. So in a nutshell, this means the daylight autonomy, the maximum daylight autonomy means when a sensor is having an illuminance level that's 10 times the target illuminance, kind of as a benchmark for uncomfortably high illuminance levels for that point. And so if a sensor is receiving this maximum daylight autonomy greater than 5% of the time, it could be an indication that is a point where this could be a liability for glare. And so the amount of these kind of maximum daylight autonomy points is set at 39% according to the simulation. And we'll go, as I mentioned before, we'll go into glare a little bit more detail in the next tutorial. And the next line in the report is useful daylight illuminance. So whereas daylight autonomy is defined as the percentage of occupied time where a sensor point is meeting a target illuminance by daylight alone, useful daylight autonomy is the percentage of time when a sensor point is within a range of target illuminances. So by default, it's the target is in between 100 lux and 2000 lux. And so this is useful for also understanding whether what area of the space is basically at a useful level of daylight illuminance, not too dark and not too bright. And so it's indicating that this area that's larger than, that has a useful daylight illuminance score of larger than 50% is 58% for active occupant behavior. And lastly, electric lighting use. And so this is left blank because we don't have any electric lighting set for our model. And I'll go into this electric lighting in a subsequent tutorial. And then the next group of information on the DASIM simulation report has to do with the simulation assumptions. And here it just gives you the description of the site, the occupancy description, as well as any lighting control or shading control for the scene. And since we don't have any lighting control or shading control, these are left blank. And again, I will go over this in future tutorials. Okay, so I'll minimize this DASIM report and we'll go back to Rhino, and you'll see that DIVA has created a false color mesh around our sensor nodes that corresponds to the values of daylight autonomy in the scene. And if I zoom out, all the way out, you'll see that that DIVA has also created a legend for the simulation that we just ran for daylight autonomy. And daylight autonomy is the percentage of occupied hours ranging from 0 to 100. And since we're in wireframe mode, I'll go ahead and change it to shaded. So you could see here that we have a color scale from 0 to 100 that corresponds to the percentage of occupied hours that meet our target illuminance. And I'll zoom in again to our reference office. And since we're in shaded mode, we're looking at the top of the building, and our false color mesh isn't showing up because the roof geometry is blocking it. So under the Layers tab, I'll go ahead and turn off the layer roof to uncover the false color mesh that corresponds with daylight autonomy. And if you zoom in a little bit closer, you'll also see that DIVA, that because I checked label all nodes, that DIVA has also populated those nodes with their corresponding daylight autonomy value. And that ranges again from a very high value close to the facade and then tapering off near the back of the space. And as I mentioned before, the daylit area can be considered the area where the daylight autonomy has a value of at least 50%. And in the case of this model, if you think back to the legend that we were looking at, or if you just look at the values that are on the nodes, the daylit area is the point, or the points that are in between red and then to the middle of the scale, which is at about yellow. And you can see that the daylit area kind of ends at around this portion of the space. And so that about wraps up this tutorial for daylight autonomy. And in the next tutorial, I will be going over visual comfort and glare. Thank you.